In this video, we're going to be discussing Lab 4, which is the enthalpy change or the heat change of a reaction. Okay, so you're going to be doing a lot of heat measurements here. So heat is a type of energy. The word enthalpy in chemistry simply is another way to call heat energy. So enthalpy is heat energy, specifically the heat generated from a reaction. Okay. So here, what you're going to do is have a reaction happen in a closed container, which is called a calorimeter. And this reaction generates heat, or it gives off heat from the reaction, and that heat that is given off is called as exothermic because the heat is coming out of the reaction. It's much like when you burn a fuel, like for example propane in the grill, right? A lot of heat is generated. So the burning of propane or the burning of gasoline are exothermic reaction. A lot of heat energy is generated. Now what happens is, if you have a closed container, that heat is then released into the contents of the container, and so there will be an increase in the heat of the container and its contents. And the way you can tell this is because there's going to be a change in temperature. So the contents of the container will include what you start out with, your starting material, the reactants, and your final products, which is the reactants getting transformed into products. So the final components present in that reaction vessel or the container, and a solvent. A solvent is something that dissolves the reactants, and that would be in most cases water. All right, so these are some of the contents. The initial materials you start out with are called the reactants, and the reactants are then getting transformed into products through the reaction, and then the heat that is generated is now being distributed into the water into which those materials are dissolved, as well as the walls of the container. Okay. So the heat transferred from the reaction in this closed container is transferred into the solvent. And what you will then do is have a thermometer dipped into the solvent or water. And so then you can note the heat being released as a temperature change, right? So this method of measuring the heat generated from a reaction is called as calorimetry, all right? And calorimetry is derived from the word calorie, and we all know that we associate calorie as the energy associated with food, all right? Okay, so when we digest or we eat food, the energy released are in terms of calories, and that is also a type of heat energy. So this closed container, as I explained before, is the calorimeter. And the calorimeter is like an insulator. It prevents that heat being lost to the surrounding, like to the surrounding air. So it keeps all of that heat generated from the reaction within itself, all right? So it basically is isolating the stuff inside, the contents inside, from the outside air and the outside environment. So now if you don't have something as sophisticated as this is called as the bomb calorimeter, then you can create a calorimeter using a couple of coffee cups, right? Styrofoam coffee cups. They act they act like a calorimeter in the sense that the styrofoam makes it it makes the environment inside and like an insulator, and therefore it insulates whatever is inside the cup from the outside environment, which is the surrounding air. Now, if you have a lid on top of this coffee cup, then of course it's a closed container. And then you can again do the same thing, have the reactants dissolved into water, and then stick a thermometer in here, make a little hole in the top of the lid and stick a thermometer in here. And then as the reaction proceeds and the heat is generated, you will see that the initial temperature, which was at room temperature, which is approximately about 21 or 22 degrees centigrade, you will see that the temperature is gradually rising as a result of the heat evolved out of this reaction. All right. So again, you will then plug it into an equation to calculate the heat generated from that reaction. This same principle is done in a more sophisticated instrument called as the bomb calorimeter. Now, here in this closed insulated chamber would be something like any kind of food stuff. All right. It could be anything. It could be a carbohydrate, a protein, chips, you name it. All right. In order to find out the calorie content of that food, what they will do is burn it inside here. Now, the heat that is released from that burning, all right, the evolved heat is then going to be distributed into the surrounding water as well as the wall of the calorimeter. All right. Now you have a stirring bar in here to make sure that the heat is evenly distributed in the surrounding water and the walls. All right. And then you will register this heat as a temperature change. So initially the temperature would be at room temperature, and then as the reaction proceeds here, as the burning goes to completion, you will see the temperature drastically rising up. Okay. So the heat transferred from the reaction to the surrounding water is calculated using this formula. All right. Q is a symbol for heat, or as we called it, enthalpy. All right. That simply means the heat transferred into the water, and that would be calculated as the mass of water times this symbol Cp is the specific heat of water. What is specific heat? Specific heat, like density, is an intrinsic property. All right. So water has a certain value for its specific heat. And the way specific heat is defined is if you take 1 gram of water and heat it up. Suppose its initial temperature was 22 degrees, and now it went up by 1 degree to 23 degrees. So that amount of heat that you supplied to make that 1 gram of water increase in temperature by 1 degree, that is defined as a specific heat. And in terms of water, it's 1 calorie per gram degree centigrade. So for every gram of water, to make its temperature go up by 1 degree centigrade, you need to supply it 1 calorie of heat. And this triangle stands for change. So it's called as delta, the Greek symbol delta. So delta T, T is temperature, all right? So the heat transferred to water is the mass of the water times its specific heat times the change in temperature of the water from, and delta T is the final temperature minus the initial temperature, right? So that's how heat transferred to the water is calculated. So the units of heat is in joules, okay? Now, if you convert a calorie into joules, it's 1 calorie is 4.18 joules, all right? So for every gram of water to increase its temperature by 1 degree centigrade, you need to supply the water with 4.18 joules of energy. Delta T is the change in the temperature of the water before the reaction and then after the reaction. Okay, and M is the mass of the water inside the calorimeter in grams. So the total heat transferred to the water from the reaction happening inside the calorimeter has two components to it, all right? One component is the heat absorbed by the walls of the calorimeter, right? So yes, the system is isolated. However, you have to take into consideration that all of the heat is not just absorbed by the water from the heat generated from the reaction, but some of the heat would also be absorbed by the walls of that calorimeter, and this is called as the calorimeter constant, all right, or it's abbreviated as Ccal. And so that heat absorbed is the Ccal times the change in temperature from the initial temperature to the final temperature reached. So this heat absorbed by the walls plus the heat absorbed by the water together, that is the total heat, all right? So heat absorbed by water and heat absorbed by the walls of the calorimeter is the total heat, and that's what we are going to be calculating, all right? So as explained in the previous slide, heat absorbed by the water is the mass of the water inside the calorimeter, the specific heat of water, which is 4.18 joules per gram degree centigrade, and then the change in temperature of the water before and after reaction. So the total heat absorbed by the water, again, is going to be the heat absorbed by the walls of the calorimeter, and then plus the heat transferred to the water from the reaction, all right? That's the total heat that the water inside is going to that's the total heat, not just of the water, but the water plus the walls of the calorimeter. So Ccal is called a calorimeter constant, and that's the first part of the experiment. We have to determine what this calorimeter constant is. The delta T is that change in temperature, okay? So that's the initial temperature before reaction is noted, and the temperature after the reaction is over is noted, and the difference between these two is the change in temperature. M is the mass of the water in grams, and the specific heat of water is 4.184 joules per gram degree centigrade, okay? So the heat of the reaction is going to be measured in this experiment. And this experiment involves the reaction of magnesium with hydrochloric acid. Now, a lot of heat is generated from this reaction. And as I said, if the heat is produced as a result of the reaction, the heat is given out, then it's called as exothermic. Exo for exit, all right? So it's coming out of the reaction. So it's an exothermic reaction. So this is the reaction. You have a piece of magnesium metal, and you dissolve it into the acid. Now both of the reactants are dissolved in a certain amount of water inside the calorimeter. And what magnesium will do is push out the hydrogen, all right? So magnesium and the chlorine part, or the chloride as it's more appropriately called, remain dissolved into the water, AQ. When you have an AQ next to the symbol of a substance, it means dissolved into water. And then that hydrogen comes out as a gas. So you'll see visually, if you could see this reaction, you would see bubbles of the hydrogen gas being generated, and G stands for gas. I'm going to have to stop the video here and continue this in the next video.